Hello, my name is Tyler Erb, and today we're going to talk modular arithmetic. Modular arithmetic has a whole range of applications when it comes to the real world in terms of encryption and cryptography. It's used a lot when we're talking about computer sciences. It also shows up on most contests you're going to do, ranging from all levels of math counts and beyond. So modular arithmetic is a system of arithmetic when it comes to integers, right? So we're dealing with positive and negative whole numbers here, and it talks about the remainder. So we don't actually care about how many times a number would go in. We care about the remainder when we're dividing. So here's my little example for you. If we were to take 17 mod 5, right? We don't care that 5 goes into 17 three times. We only care about the fact of what's the remainder, right? We know that this would in fact be 3 times 5 plus 2, right? That's congruent to 17 mod 5. But when we're dealing with mod 5, this 5 really becomes a 0. So this becomes 3 times 0 plus 2, which just simplifies down to 2. So we know that 2 mod 5 is congruent to 17 mod 5. We could also take this back even a little further, and we could subtract another 5 from this and make it -3 instead. Another way to think about this is you could really say that 17 is congruent to 5 plus 5 plus 5 plus 2, and say all of these 5s are going to be equal to 0 when we're dealing with mod 5, and so this would just get us 2. So again, we see this wrapping around feature. So let's talk about some of those applications. So where can we use modular arithmetic? You can use it on Euler's-Toshin theorem, Chinese remainder theorem, which you might know from, you don't know how many marbles you have and you make it in groups of 7 and you have a remainder of 1, or make it in groups of 3 and you have a remainder 2, right? You can use it in Diophantine equations, which we're going to use today, digit problems, last digit, units digit, even units and hundredths digit, as well as Wilson's theorem, Lucas's theorem, Hensel's lemma, and general cryptography, right? We're going to focus today on Diophantine equations and digit problems, but you can see it pop up in a number of ways. And even when we're dealing with digit problems, we really can use Euler's-Toshin as you get higher and higher up. So this is a more formalized way of what we're talking about, right? If we take d, mod little d, what we're saying is that we can divide little or big D by little d, and it goes in evenly q times and has a remainder of r. Our answer is always going to be this remainder. And notice how this remainder is going to be a positive integer, right? It's going to be somewhere between 0 and the absolute value of d minus 1. We always want to kind of end up on that positive number, even though the negative would also be congruent. For our example here, 2022 mod 60, well, we can divide 2022 by 60, and that goes evenly 33 times and has a remainder of 42. So our answer would be congruent to 42. If we wanted to, we could also subtract another 60 here and realize that we have this equivalence of -18, right? -18 would also be congruent mod 60. So keep that in mind. Our final answer here is 42, but -18 we could use kind of as in our in-between work. So another example here that we could talk about is just dealing with these cells. So this cell kind of structure that I'm dealing with is mod 9, right? And so this is going to change depending on what mod you're dealing with. But we know that 0, 9, and 18 are all going to be congruent mod 9. And also -9 and -18 will also be congruent. We can do the same thing with 1. It would be -17, -8, 1, 10, and 19 are all going to be congruent here. Notice all we're doing is in between each one of these values, we're just adding our mod, right? So in this case, it's mod 9, so we're going to add 9 to get from 1 to the next. Because really when we're adding our mod in, we're adding in 0, because 0 mod 9 in this case is congruent to 9 mod 9. So let's try a couple more problems out. So let's look at some basic addition and multiplication problems. Sometimes when we're dealing modular arithmetic, it'll actually be easier to simplify your addition first and then take the modulus. Other times it might make sense to take the mod first and then simplify. In this case, if I'm adding 17 and 34, I'm going to get a sum of 51. And if we're doing 51 mod 5, I think it's pretty easy for us to say Well, that's going to go in 10 times, but we don't care about how many times it goes in. All we care about is the remainder, which in this case is 1. Now, our other way is we could take 17 mod 5, which would just be 2, and 34 mod 5, which would be 4. And if we add these up, that would give us 6. However, we want the most simplified version of our answer, and so because we're doing 6 mod 5, we'd actually have to simplify this down to 1 mod 5. So again, either way, we're getting 1 mod 5, though in this case, I think it's easier for us to deal with the addition first and then simplifying because the numbers are decently small, right? You can imagine if we were dealing with this and it was maybe say like both of them were 6-digit numbers. Well, it doesn't really make sense for us to do the addition first when really all we care about is what's going on in that units digit. Let's look at this multiplication problem. If I wanted to, I could multiply these first and get 578, right? Which again, I'll be honest, I don't know the multiples of 17 off the top of my head, so I'm not cool like that. But once we take 578 mod 5, we really only care about our units digit in this case, and that will give us a remainder of 3. So this becomes 3 mod 5. Again, here I'd either have to do long multiplication by hand or I'd have to have a calculator available. So let's see what this would look like if we just took the mod first, right? If we're dealing with the mod first, instead I would take 17 mod 5, which as we saw earlier was 2, and 34 mod 5, which is 4, and we're able to multiply these together to get 8 mod 5. And because again, we want the smallest number possible, that just simplifies down to 3 mod 5. Because when we divide 8 by 5, we get a remainder of 3. And so either way, we can do this. However, if I don't have a calculator, right, it may be easier for me to take the mod here first. So problem number 1, what is the remainder of 2022, or sorry, of the 2022nd term in the Fibonacci sequence divided by 3? And we're going to define the Fibonacci sequence as starting with 1, 1. And to figure out essentially the next term of the sequence, we're going to find the sum of the previous 2 terms, right? So the next term here would be 2, because 1 plus 1 is 2. And then 1 plus 2 would be 3. 2 plus 3 ends up being 5. 3 plus 5 ends up being 8, and then 13, and then 21, and then 34, and then 55, and then 89. And you know, if I wanted to, if I had a whole bunch of time on my hand, maybe I actually find the 2022nd term and then divide it by 3. However, I don't have enough time on my hand, so instead I'm going to start looking at the modular arithmetic here, right? We know we might want to use modular arithmetic because it's talking about a remainder, and it's talking about divided by 3, right? So we're dividing by a whole integer, and we are also looking at only the remainder. So that kind of helps our cause a little bit. So if I take this first 3 terms, right? 1 mod 3 is still 1, and still 1, and 2. Now, when I add up 1 and 2, this will then give me 3. But because we're dealing with this mod 3, that's actually equivalent to 0. And 2 plus 0 is 2, and 0 plus 2 is 2, and 2 plus 2 becomes 4, but again, we're dealing with mod 3, so that becomes 1. 2 plus 1 is 3, which is 0, and now 1 plus 0 is 1. And, oh, if we keep doing this, we're going to get 1, 1, 2, 0, and oh, I bet you probably recognize the pattern back here. Let's look. Our pattern starts to repeat after this final 0. And so we don't have to keep going, right? We can essentially just look at this and say, well, how many terms are in this sequence? 1, 2, 3, 4, 5, 6, 7, 8. So after 8 terms, what's going to happen is we're going to get that repeat. So if I take 2022 mod 8, again, the reason I'm doing mod 8 here is I have 8 terms before this pattern repeats. That's going to get me essentially 6 mod 8, right? So essentially I divided 2022 by 8, I got a remainder of 6. So if I look at the 6th term in this sequence, then I will have what the remainder is when divided by 3. So 1, 2, 3, 4, 5, 6, and I get 2. So our remainder of the 20/22nd term in the Fibonacci sequence. So our remainder of the 20/22nd term in the Fibonacci sequence should be 2. Now, you also do have, this is a great problem to guess if you're ever doing a math contest, because you really only have like 3 guesses here, right? 1, 0, or 2. So the worst case scenario, even if you're like, I don't know how to do this, you should throw a guess down. Okay, so we want the smallest possible value of x plus y if 43x plus 85y equals 2022, if both x and y are integers. So we're restricted with integers, right? We can't have any fractions here. And we want the smallest positive value. So we don't want to try to just get some big negative sum, right? We want the smallest positive value. So if I'm looking at something like this, one might be like, okay, how am I even going to attack this? Or how do I know modular arithmetic is going to be in play here, right? So we essentially are only looking for a solution. And we know because this is a line, there are infinite solutions and there must be infinite integer solutions. But we're looking for the smallest positive value, which means we're looking for something relatively close to either the x or y axis. And we know that it's going to be an integer, so it essentially has to go into x, or it has to go into both x and y nicely. So if I'm looking at something like this, I have 2 options. I can either take something mod 43, or I can take it mod 85. Well, let's look at if we do this mod 85. If I take this entire equation here, right? So 43x plus 85y is equal to 2022, and I do the whole thing mod 85. Well, what ends up happening? The 43 isn't changed, right? I can't do anything with the 43 because 85 doesn't go into it at all. This becomes 0, so that's helpful, right? I've eliminated a variable, and that's kind of what we're trying to do here. And then I take 2022, I divide it by 85, and get a super gross, well, not super gross remainder. I get, let's try it again. I take 2022 and I divide it by 85, and I get a remainder of 67. Mod 85, right? This looks so much better. Look at this. We now only have one variable. Wow. Here's the problem. I don't know my mod 85 table that well, and I may be able to change this to maybe a negative 42 instead, right? If I wanted to subtract 85, I don't know how that's going to divide 67. So maybe this isn't the best mod to use, right? Let's instead try using mod 43, because that's kind of our smaller coefficient. And you'll find that a rule of thumb here is always to use your smaller coefficient, whatever that may be. So we're going to do this as mod 43. And so this whole thing becomes 0, which we saw with the y last time. 85 becomes 42. Ooh, that's super exciting. And 2022 becomes 1. Well, I don't know about you, but this looks a lot easier for me to deal with. So remember when I essentially said if it was 85, I could subtract an 85. I'm going to do the same thing here. And I'm actually going to subtract a 43 y from both sides, right? Which is the same thing as subtracting 0, and make this negative y is congruent to 1 mod 43. And again, we want y, not negative y, so I can divide both sides by a negative and get y would be congruent to 1 mod 43. Now, I know we talked about this being, we only want to use positive numbers here, right? But when we're looking for the smallest positive value and we're dealing with actual coordinates, it's possible we could have negative values. So our 2 things that we're going to deal with are either y is -1, or what if we were to add 43 to this and get a 42, right? Those are kind of the 2 we're going to use. Now, you might be thinking to yourself, well, what if we continued adding 43s or continue subtracting 43s? What ends up happening here is you get a larger and larger difference, right? And the further away you're getting, you need bigger quantities of x and bigger quantities of y, and they actually won't create a smaller sum. So once we have these 2 y values, we're going to go back to our regular equation, and we're going to plug them back in. right? No modulus, we're just gonna plug them in. So this becomes plus 85 times -1, and that will equal 2022. So we're gonna add 85 to both sides. And then all we're gonna do is divide by 43. And this will get us x is congruent to 49. So we see instantly that this goes in evenly, which great. If it didn't, we have some bigger problems. But 2, this gets us a sum of x plus y as 48, which isn't great, right? That's a pretty large sum. Maybe it's the smallest, but we should still probably try 42 here. So if I do 42, I'm going to do 43x plus 85 times 42, and that will equal 2022. So 85 times 42 is 3,570, which I'm sure you all knew off the top of your head. And I'm going to subtract that over and then divide by 43. So 2022 minus 3,570, divide that by 43, and I get x is -36, which again, it goes in nicely, right? We're getting integer coordinates, so that's good. We know we were doing something on the right path. So x equals -36. And because I'm trying to find this sum, that's actually much smaller, right? We're going to get a sum here of 6. So we can stop there. We know our smallest sum that we're going to get is 6. Again, if you go further out on your y or further out on your x, you're going to run into some issues. Also notice here, I think it's important, you can see that these values are 43 away from each other, right? Because here we're dealing with mod 43, and these values are 85 away from each other, because in this case we dealt with we're dealing with the 85 from the y. So notice how your x's are going to be 85 off and your y's are going to be 43 off. And so if you go out further, you're going to keep adding 85s or adding 43s, and you're not going to really get anywhere. All right, let's try looking at digits. So now we're looking at the units digit of a number raised to power n. So if we're looking at something like this, we're really only looking at the units digit. We don't care about anything else, right? So I'll be very helpful here and do the ones for you. So 1 to the first, 1, 1 to the second, still 1. Yep, still 1. Wait for it. It's 1. And I know you can't believe it. 1. Wow. So this has a period, right? Essentially how long it takes to repeat of 1. If we do the same thing for 2, though, here we're going to get 2 to the first is 2. Then 2 squared is 4. 2 cubed is 8. And 2 to the fourth would be 16. But again, I only care about the units digit, so I'm going to get 6. So now instead of doing 16 times 2, I can just do 6 times 2, which gets me 12. And I only care about the units digit, so I see 2. And we realize once we have this 2, 4, 8, 6, and goes back to 2, once it goes back to 2, we're going to just keep repeating. So this has a period of 4. Take a second and pause right here and see if you can figure out the rest of this table. Okay, so this is the rest of our table filled out. You'll notice that our biggest period that we could potentially have is 4. If you want to kind of prove that that's going to be the case, you could deal with Euler's-Toshin theorem. I think that would be a great way to go to show that that's really what you're going to be dealing with. The other thing to talk about here is this is specifically only dealing with units digits, right? So this is really like 1 to the n, but this also could be 51 to the n, right? And that would have the same units digit. Because we're only caring about the units digit, we're really doing all of this as mod 10. We could do the same thing with 2. That could be 3,472. If we're dealing with that to any power and we only care about the units digit, only really going to care about that 2. So the other numbers aren't going to be of consequence. So let's look at 2-digit problems and see how those are a little bit different from what we've dealt with so far. So here's problems 3 and 4. We only care about the units digit of 2022 raised to the 2022. I hope you've seen the theme. The theme of this entire lesson is 2022. So because we only care about the units digit, we can get rid of all of this. And as we just discovered, we realized that it will take essentially 4 numbers before we're going to go back to 2. So essentially, we know that 2 to the 5th is going to be congruent to just 2. So we can take this whole thing, this 2022, and do it mod 4. And so if we take this whole thing mod 4, we're going to get just 2. And so this entire problem, right, 2022 raised to the 2022, can simplify just down to 2 squared. Again, I did the mod 4 because it takes essentially 4 digits for 2 to repeat. And if you tried to look at it, you would see it go just like we just did, 2, 4, 8, 6, 2, 4, 8, 6, 2, 4, 8, 6. And so we can just take that power mod 4 and end up getting 2 squared, or 4. So our units digit for that number would be 4. Let's look at this one. So here we're dealing with the last 2 digits of 504 to the 4044th power. So here we're looking at the last 2 digits. We can't simply just deal with only 4, right? We have to deal with the 0, 4 and kind of see how that's going to play out. We could do Euler's-Toshin and try to figure out how long this would, what we could divide 4044 by to really figure out a kind of a shorter path. But as is always very responsible with math, you might just want to do a little bit of casework. So we don't care about the 5, we only care about the 04. So what I'm able to do here is, again, just take the 4 and repeatedly multiply it by itself, right? Repeatedly multiply by 04. So this gets me 16, then 64, and then 64 times 4 is 256. But I don't care about the 2, I only care about the 56. Notice how this will make our problem a little bit easier, but it's still going to take us some multiplying to do. Also notice how we're having this alternating 4 and 6 happening, right? 0, 4, and 16, 64, 56, 24, 96. And you saw that just looking at the units digit. But when we're dealing with something like this, we really want to care specifically about both digits. So I'm going to keep multiplying while I'm talking. We also could try to figure out how many possible combinations of 6 and 4s we could have, right? That's an easy problem to do. But right now, I'm just hoping that we'll eventually find this pattern. And it takes a little bit of time, but we do, right? After 76, we multiply by 4 again, and we get 04. So here we see that this is going to repeat after this pattern. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This takes 10 for us to repeat. So if we do 444 mod 10, because that's how long it took for the powers to repeat, this would give us just 4. So I could take 04 to the 4th and get 56. Now, one thing I want to keep in mind, it did talk about the last 2 digits here. So if we'd somehow gotten like 04 to the 1st, you would have to write, I keep saying I mean 0. You'd have to write the 0 and the 4 together. You can't just say 4 because it asked for the last 2 digits. In our case, our answer is 56. But again, always watch out if it's talking about digits, you might need to use that 0. Well, thank you. And if you have any questions, please reach out.